Hello ladies and gentlemen, boys and girls. Imagine for a moment that you have stone in your hand and you throw that stone at a certain angle. Now, if I ask you what kind of shape that stone takes in its entire journey, what will you say? You will say that Shivam, it is parabola, right? This is very much evident from that shape. But now, if I ask you, will you be able to prove it? Well, if you know the answer, then congratulations. But if you don't know, then don't worry. In this video, we are going to prove that why when you throw that stone, or for that matter any other object in that fashion, it takes a parabolic trajectory only and why not any other shape. So for that purpose, we have divided this video in two parts. In first part, we are going to look at what exactly happens to that object in its entire journey, and in second part, with the help of some mathematics, we are going to prove that why the shape taken by that object is parabola only. So let's get started. Now let us try to understand the physics behind it. Imagine for a moment that you are standing in an open field and you have stone in your hand and you throw that stone in a fashion I mentioned earlier. Now, when you throw any object, you actually impart a force on it. And that force, in our case, is actually tangential to that curve. Meaning, if you want to find that force on that curve at any point, you just have to draw a tangent at that point. You will get the direction of that force. Let F be the value of that force in our case. And very interesting thing happens with this force. But before getting into that, let's quickly make three assumptions. The very first assumption is the air resistance offered to that projectile or to that object is very negligible. Why I made this assumption? I will soon get to that. The second assumption is the maximum height reached by that object is very small as compared to the radius of the earth. Now when I am saying this, I am indirectly saying that the acceleration due to gravity is constant throughout the flight. Because if you have studied the formula of acceleration due to the gravity, it actually depends on the height above the Earth's surface which is covered by that object. So when the height is small, the acceleration due to gravity, the variation in acceleration due to gravity is very negligible. The third assumption is the horizontal distance covered by that object is very small as compared to the radius of the earth. Now again, when I am making this assumption, I am indirectly saying that the turning effect of the earth, the rotation of the earth has very negligible effect on the trajectory of that object. Now if you look at the image carefully, you may have noticed something. The object is covering horizontal distance. At the same time, it is also covering vertical distance. Now, many of you watching this video may have got it. The force which you actually imparted on it initially is actually getting split into two parts. The first part and the horizontal part is actually responsible to give that object the horizontal motion, and the second part, the vertical part, is actually responsible to give that object the vertical motion. Now, there's very interesting thing to note about these two forces. The horizontal force throughout the journey of that object remains constant. Why? Remember our first assumption? We have assumed that the air resistance offered is very negligible. So there is no opposition to that force, to that horizontal force. But same is not the case with vertical force. There is a big opposition to that force. And that force, ladies and gentlemen, is gravity. So what exactly happens when the object ascends from point O? Initially, the value of the vertical component of the force is very high. So you can see the portion of the curve from point O to point S is steep. The reason being, the rate of the rise of the object is very high because the force is high. But don't forget that the vertical component of force is constantly counteracted by the force of gravity. So you can see the portion of the curve from point S to point P is flat, since the rise of the object is slow. And at point P, the vertical force becomes 0 and gravity says, time up baby, and the downfall begins. But during descent or during downfall, exactly opposite happens. This time, the vertical component of our force is not against the gravity, it is with gravity. But since it has just got 0, so it takes time to get back to its initial value. So you can see the portion of the curve from point P to point T is flat because the rate of the fall of the object is slow. But gradually the vertical component of the force starts to raise its magnitude, and you can see the portion of the curve from point T to point Q is steep because the rate of the fall of the objects becomes fast. And at point Q, finally the object hits to the ground and it transfers all its energy to the ground. And the value of the vertical component of the force at that point become equal to its initial value, the value which it had when the object just took off. And its entire journey, in the entire journey of that object, the horizontal component of the force remains unaffected. Now I'm very sure that after watching this video, next time when you throw any object in that fashion, you will be knowing exactly what is the physics behind it. And I'm sure you're eager to learn the mathematics part of it too, which will be very simple. And in order to do so, don't forget to watch the part 2 of this video. And like, share and subscribe my channel, and don't forget to hit that notification icon so that you will get the updates of my latest videos. And last but not the least, always remember, make learning interesting. Thank you.